Okay, I'll try to solve it. Let's do our best. Okay, so what we're saying is that we differentiate. This is an approximation. That's something that we learn basically. These are constant that we're trying to determine. So we make this product and we obtain that divided by L. And you see that's basically the elongation divided by the original length. That's basically the definition of the strain. Okay? So I wanted to show you that. Now, let's go on. So we can say is that the force P at every point is going to be equal to EA, see, from here, times D2x minus D1x and divided by the length. These are local. Okay, this is just an approximation. Okay, now you see that because of the interpolation, this is a linear interpolation, the result here is that the force, the internal force in this element is constant. So P is constant in the element. But this is not correct for every case, and we will insist on that. Okay, there are some cases where this is adequate, but there are other cases where this is wrong. And when it is wrong, that means that our approximation is not correct, error. We have to be aware of that. Okay, now let's go on. We have done that, and we are starting to remember. Let me go back to remind you about the title of this subchapter. The title of this subchapter is to deduce the stiffness matrix of the bar element, okay? And this is what we're doing, okay? We are going to deduce the expression for the stiffness matrix of the bar element. Okay, let's do it. It's saving just in case this gives us a problem. And as I said before, we're going to have another interruption in 40 minutes. Okay, so now, since we are working with, since this is a discretization, we will be interested only in the equilibrium of the joints. Okay? What happens in between? This is discretization. We only worry about 2 points, the equilibrium of 2 points. And the rest, well, we'll see what happens in the future. But so far, this is what we are interested in. Okay? Damn it. I lost my, here it is. Okay. So, this is the situation right now. This is the beam. Let me draw a thick beam like this. This is the joint. This is the joint. And here I have external force. Here I have an external force. Okay. In between, I don't care. And what we are going to do is make a cut about here, very close to this joint, and another cut here, very close to this joint, and we're going to try to establish equilibrium around here and around here. Okay, so let's do it. So we have, I'm going to draw with a large dimension. Here is the joint. I have this external force. please, this is external force. External force positive points to the right. Okay? This is a positive phase. So on the positive phase, P points to the right. Now, for the equilibrium of the ordered joint, I have something similar. Okay? Here is the joint. This is the external force. And this is a negative phase. In the negative phase, P points to the left. See, when you make a cut, remember, positive and negative phase, the internal forces behave differently. But now, the thing is that both this piece, this end, and this other end, they both have to be in equilibrium. So we say equilibrium of left joint. So we have this plus that. So we say F1x plus. Who is P? Let me go back just a little bit. P has been approximated by this. So let me go back here. If I multiply this by EA, okay, I have P. So I'm going to use this expression here. But I need more space, so let me go on the other line. Okay, so this points to the right as positive. You said plus. And here I have EA minus 1 over L, 1 over L, and this is multiplied by D1x, D2x. So this is the equilibrium of the first joint. The second one. For the right joint. Okay, we have this minus EA is going to be the same. So it's going to be minus 1 over L, 1 over L, and then we have this is equal to 0. So what we do now is we put the whole thing together. Okay, so we say, okay, we take this term from the equilibrium of the first joint, we put it to the right, of course with negative sign. And this one here to the right, and with the negative converted into positive. So we can say that F1 is going to be equal to, the negative, I will put it inside. So it's going to be EA 1 over L minus 1 over L and times D. And the second one, we take this to the right and say F2x is going to be equal to EA, is going to be equal to minus this is positive. So these two equations specify the equilibrium of one and the other joints of every bar. So let's put it together. Okay. See, putting the two equations together. So on the left, I have a vector. These are the vector of external forces applied on the joints. And it's equal to, we get EA divided by L. You see that L is in the denominator of every term. And then here, I have D1x, D2x. Now, from the first equation, I have 1 and minus 1. From the second equation, I have minus 1 and 1. Questions so far, people? Questions? No? Okay. Now we're going to identify things here. Damn it. This is what we call the stiffness matrix of one single element. And you see that this hat means that we are working in the local reference system. Okay, in the next session, we'll consider that we need to express this equilibrium in a global reference system. And in that case, we're going to take this hat out, but we have to do a transformation. We will explain that. Okay, so we can say that the external forces on the joints is equal to the stiffness matrix of the element multiplied by the joint displacements. Okay, this is external forces. This is joint displacements. Okay, and who connects these two? This is what we were looking for. This is the stiffness. I don't know what happened. Matrix of bar element. So it's E joint modulus A constant area of the element. That's the length of the element. So all of this is known. We have two unknowns. Questions, people, so far? What's the value of the determinant of the stiffness matrix, people? What's the value of... Yeah. What's the value of the stiffness matrix? Of the determinant of the stiffness matrix. What's the value of the determinant of this?
0.
0, yes. That means that if we take the problem just like this, we are not able to solve it. And that's because we have not applied enough support conditions. Okay, let me try, because I have problems with this thing. Let me try to write it with different color. Let's see if I can try with green. Okay. Not this. No, I couldn't. Jesus Christ. Let's see here. Now. Notice that the determinant of K is 0. okay? This is because we need boundary conditions that supports to find a unique solution. Okay, so if you do not apply boundary conditions, you will never be able to solve this problem. Let's suppose we apply an example. Let me stop because I need more spaces. Damn it. What happened? Oh, shoot. Damn it. Jesus Christ. Just a second, please. I'm trying to. Damn it. Okay, let's develop an example so you can see the way to apply these things. Okay. Okay, so let's see. I can find this here. Okay, let's find the solution to this problem. Okay, now, of course, this is extremely easy, but let's see what happens. Okay, now, of course, we're going to discretize. It's easy. Okay, we're going to consider 1 and 2 joints, obviously, right? So this is the first element. There is only one, of course. We have EA. These are the properties of the section. So what can we say? We can say is that according to this, the left end doesn't move. So immediately we can say that D1x is equal to 0. So we see that the left end does not move. That means that D1x is equal to 0. And this is something that we need in order to take the singularity away from the problem and be able to find a solution. See, so if remember when we solve the solid mechanics problem, that you need to specify at least enough geometric boundary conditions. In this case, this is a 2D problem. Then, I'm sorry, it's a second order problem. That means that you need to specify at least one point where it doesn't move. That's a geometric boundary condition. Now, the other boundary condition could be either geometric or natural. In this case, we know the force which is being applied on the right end, right? So we know that the force is F. But at least we know that 1 point doesn't move. So let's do the second boundary condition. So we can say that on the right end, we know that P is equal to the force F. Okay, so what is going to happen is that this is an external force, but it's also known. Since it is known, that means that we know it. That means that it can be applied, can be considered as a boundary condition. Okay, so we can say that using 1 bar finite element, the equilibrium will be what? E A over L. I have 1 minus 1 minus 1, 1. I have here D1x, D2x, and it's equal to F. I'm sorry, this has to be little. So it's going to be F 1x and F 2x. Okay, now we know that this is 0. And we know that this is plus F. So we recognize here that we have 2 equations and 2 unknowns. And the unknowns are F1x. Remember, F1x is the external force that is going to be applied on the left end in order to have the system in equilibrium. And D2 is the displacement of the right joint. Okay? So we can proceed now to solve it. Now, there's a question?
Yes,
Okay,
Nevares.
okay. Go on.
Why do we have the same stiffness matrix?
Because we have one single element. This is the system that we want to analyze, right? And right now, see, just because this is a first example in this semester, that we're going to take the whole bar as one element. Later on, we could use and split it into more elements. But right now, let's suppose that we take one element from here to there. So we have proved that this is the equation that we have to satisfy to have equilibrium for both joints. So this is what we apply. And what we have to do is we have to identify that the 1 here is the joint on the left, and the 2 is the joint on the right. That's all. So in this case, that's what I wrote it here. See, this is the 1, this is the 2. Of course, we have to apply the correct values of EA and the length. And eventually we have to determine, or we have to apply the known value of the force. But that's all. Okay? Now, before we solve it, there is a very important step here, okay? You recognize that we have one unknown on the right, and the other unknown is on the left. okay? So it's like considering two subsystems, okay? And one subsystem is going to be the one which has the displacements as unknowns, okay? We can write this thing. Let's identify two subsystems. The one with unknown joint displacement. And the second with unknown external joint forces. Are you with me, people? Okay, so what we do here is we first solve for the solution of the unknown displacement. We solve first for the unknown displacements. So you see that if we take the second equation, that's going to be the first subsystem. I'm going to write it here. So this is going to be EA over L. We take the second row, so it's going to be minus 1, 1. It's multiplied by what? 0 and d2x, and it's equal to plus f. You see here that f is known and d2 is unknown. So this is the first subsystem. And it's easy to solve, right? Because we can immediately see that d2x, so we take this to the right, so it's going to be f. I just received a notice that we will stop in 10 minutes, so be ready, please. There. Okay? So that's that. And then we have to go to the next step. Next step is, Jesus Christ. Damn it. So we have the equations, finite element equations. We apply boundary conditions. We recognize the differences between these two subsystems. We solve for the first subsystems, so we know now all the displacements in the system. We can write it here. Notice that at this point, all joint displacements are known. All are known. So what we have to do now is to proceed to calculate the unknown forces. So we can calculate the unknown forces from the second subsystem. So let me go back if I can, because I'm having trouble with these things. So we're going to take this, the first equation. So here, so you have EA over L, 1 minus 1, and on the right we have F1. Okay, so let's write it. So we have EA over L is 1 minus 1, 0. And D2, we know this, so it's going to be F L divided by EA. And on the right, that's F1X, like that. So we make this product. So we say EA over L. So we have this multiplied by that. So it's going to be minus FL over EA. And that has to be equal to F1X. We cancel. And we say that F1X is equal to minus F. People, questions? People, questions? Is there any question from anybody?
No.
No? Okay. So as you can see here is that we have this, damn it again. This is fixed. This is on the right. And what we have found is that this end has moved to the right. And this is what we call D2X. And this is F. And we have found is that on this end, we have this force, which is pointing to the left. So the support generates the force F, which makes sense. Okay? Now, finally, we could try to specify the displacements. Okay? So we know D1, which is 0, and we know D2, which is FL over EA, we can set up the displacement function. Okay, so this is what we're going to be doing now, if I can. So remember, this is 1 minus x over L, x over L. This is multiplied by d1x, d2x, right? This is something that we assume, because this is not correct necessarily. In this case, this is 0, right? And the other one, we just found it. So this thing here is equal to FL over EA. So we can multiply and say, so the approximation that we have found is that the displacement of every section is equal to, okay, this is multiplied by 0, so this else disappears, so we get F over EA times X. So we could draw and this function is going to be 0 here and linearly increase here. There. The analytic solution, I'm not going to do it, I'm just going to set up, is that the equation that we have to solve is this. In this case, how much is f of x, people? How much is f of x? How much is f of x?